Good morning, everyone, and thank you for your time and attendance this morning. Just wanted to start off by saying we understand during these difficult times that the new norm has been changing. We want to be able to provide you with the knowledge and expertise of our local sales and service centers, as well as let you know SwageLock globally as a company is here to support and deliver the same service we had prior to these challenging times. We know your time is valuable, so we're going to begin our session at 10 a.m. sharp. So I just wanted to give a 5-minute intro before the session begins. Thank you everyone again for your attendance. Good morning again, everyone. So we'll begin in a couple minutes. Just give everyone's a couple more minutes to get online, and we'll start at 10 a.m. Thank you again. Okay, let's get started. Welcome to our Level 1 Regulator virtual training. I'll do an introduction of myself first. My name is Katie Whitman. I am the Marketing Specialist for SwageLock Southwestern Ontario. I joined SwageLock Southwestern Ontario 7 years ago, beginning my career as a CSR. Moving into some warehouse support, and for approximately 4 or 5 years, I've been supporting us as a marketing representative. I'm going to pass this on to Jay Matusi, who is one of our sales representatives and our trainer, and he's going to tell you a little bit about our local distributorship in its own. Go ahead, Jay.
Thanks, Katie. My name is Jay Matusi. I've been with the distributorship for just about 17 years. I held a variety of roles, and my current role is inside-outside sales rep, and I also handle all of the training requirements at our customer sites. A little bit about our distributorship. Swagelok, Southwestern Ontario, services the Sarnia area, as well as Windsor, Essex, all the way east to Hamilton, Burlington, Oakville. We also cover the Niagara region and up north to Bruce County. So that's our territory. The industries we cover, core industries would be petrochem, refining, steel making, power generation, both nuclear and fossil fuel, semiconductor, and automation. Our core products, just a brief snapshot, but certainly not limited to the entire offering, are tube fittings, valves, hoses, quick connects, and the subject of today's discussion, pressure regulators. We've also branched into services. About 15 to 20 years ago, we began custom solutions, which involves panel assembly and skid and fabrication sub-assemblies at our shop in Sarnia. And we also have a field services component to our services, and those include compressed gas leak detection, hose evaluation, and sample system evaluation. I'm going to turn it over to Rich now, who's our field engineer, and he's going to take over and perform the presentation.
All right. Good morning, everyone. Thank you for joining us. Thanks, Katie and Jay, for that introduction. So I'm Rich Wubbs. I'll be your presenter today. And I've been with Swagelok for over 20 years in various engineering roles, starting with the factory. And for the last 12 years, I've been working with the distributorship doing custom solutions and field engineering work. So I want to talk a little bit about field engineering before we start talking about regulators. The really neat thing about Swagelok's field engineering group is that we have a worldwide group of engineers. There's over 100 of us. And we've got real life field experience in various fields that we can translate back and forth and share within the group. So when we have a challenge with a customer challenge, we can share that, get some feedback from the group, and come up with a really good solution that more than likely has already been seen and tried somewhere in the world. As part of that group, we do detailed on-site evaluations. And some of those evaluations are very simple. They're as simple as myself coming to your site, having a walkthrough with you and identifying some of the challenge areas and some of the potential solutions that we can offer. All the way to a complex week-long 4-person survey where at the end of the week, you receive a very detailed report about what was found, what the challenges are, what some of the potential solutions would be, and also a ranking of those challenges that are within the report. So you can target the most important items first, be it safety or cost recovery. So keep us in mind when you have these challenges. Please get in touch with us. We're more than willing to come on site and have a look. You may be wondering these days with the current visitation restrictions with COVID-19, how we could accommodate that. And what we've been doing is we have been doing virtual surveys. So one field engineer will go in. We'll have a number of other field engineers that are networked in but off-site and able to provide feedback and gather information. So today we are talking about regulator basics. A few housekeeping things before we get started. Since we're doing this as a Teams live event, you do not have access to your microphone or your camera. So I cannot see or hear you. So if you have questions, if you could please use the chat feature, and please post those questions as we have the discussion. Jay will be fielding those questions. We'll address any that Jay could not answer at the end of the presentation. Please contact your Swageock account manager if there's anything that we didn't cover, or if you have other challenges that you'd like us to have a look at. And last of all, thanks again for attending today. We really appreciate your time. So this is our agenda. We'll talk about the basics. Then we'll talk about the theory of how it operates. Then we're going to look at the flow curves, and finally some performance tips and tricks, how we can get the best out of our regulator. So first of all, what is a pressure regulator? And this may seem like a silly question, but this is important to formulate the rest of the presentation, and that is that a pressure regulator is a mechanical device that's designed to control either upstream or downstream pressure, and the key is pressure, in response to system changes such as flow pressure and temperature. So this is really important. The regulator is intended to control pressure only. It's not a flow control device. It's not a temperature control device. You will see changes in flow based on the responses that the regulator has in order to maintain pressure. However, it's not controlling flow. It's controlling pressure. So that's a really key difference. And just to bring that home a little more, on the left here we have control valves. Control valves, they're for adjusting flow. They're not for adjusting pressure. They need some sort of external feedback in order to do their job, typically. Whereas regulators, on the other hand, they do control pressure. And what's really neat about a pressure regulator, it is self-contained. It has its own internal feedback mechanism that allows it to adjust pressure and maintain the pressure that you want it to maintain. There are regulator setups that have external feedback. We're not talking about those today, but a regulator in its most basic form, just a nice little device. So we're going to talk about two types of regulators, and it really has to do with the side of the regulator that they're controlling, the side of the process that they're controlling. We have pressure reducing regulators on the left-hand side of the screen. And you'll find a lot of times I'm going to refer to these as forward acting regulators. And on the right-hand side of the screen, we have back pressure regulators. So the whole idea is that ultimately we want to control what's happening with the pressure inside the process. In order to do that, if this process, for example, requires 100 psi, and we have a 3000 psi source of pressure here, what this regulator is going to do is, through the mechanism that it has internally, will reduce this pressure coming from the bottles, will reduce the pressure to 100 psi as it goes through. On the flip side, when we're venting our process, we want to be able to maintain this 100 psi inside the process. So conversely, while this was dropping pressure as it ran through the regulator, this back pressure regulator is actually maintaining the pressure in the process. So as this flow runs through to atmosphere, that we maintain our 100 psi on this side and 0 psi on that side. So a back pressure regulator is almost, you could consider it to be a very precise relief valve. It's not a relief valve, but a similar sort of operation. But the difference is that a back pressure regulator is really intended to flow all the time, not just in periods of overpressure that are unplanned for, unrequired in the system. So, basic regulator theory. There are basically three parts to a regulator that we're going to be looking at today. And number one, we have the sensing element. So this is the part that actually takes that pressure and then translates it to the rest of the mechanism. In this case here, we have this thin metal diaphragm. We have a loading element, which in this case is this range spring here. In some cases, it could be compressed gas. And third, we have the control element, which is essentially a needle valve that is built into the regulator, and that is what opens and closes to modulate the flow and pressure, to control the pressure to the outlet of the regulator. And so we have the seat, and then we have the poppet is the actual moving valve mechanism. So there are two different types of sensing element that we could have. Number one, we already saw that in the previous slide, is this thin diaphragm. In this case, it's a metal diaphragm. It could be an elastomer in some cases. The other style is a piston style, which is a machined piece of metal, typically, that is sealed with O-rings or quad rings. And then you have your sensing area underneath here. Similar here, we have a sensing area underneath this diaphragm here. So the difference between the two is that with a thin metal diaphragm, you have essentially almost zero friction created by that sensing element. So you have really, really good sensitivity. On the flip side, you do have some pressure limitations because of the thickness of the material. So with a piston, you do have higher pressures that you can achieve. The trade-off is that because there's more friction involved, it is less sensitive. So as in any decision-making process, there are always trade-offs, and regulator selection is no different. The diaphragm regulator, especially with a metal diaphragm, you're going to get better compatibility because it's metal. Whereas with the piston sensing, you're going to have some elastomers involved, so you have elastomeric limitations. So it's good to understand these differences, and it helps us to select the correct regulator for the application. So if you do have a high pressure, then you'll need to go to a piston. If you've got lower pressures, you typically want to default to a diaphragm type regulator. So, how does this self-adjustment in a regulator work? Well, it's something that we call the balance of forces. And we have an equation down here. We are going to be doing some math through this presentation today. So we have basically this F1 is going to equal the sum of F2, F3, and F4. You'll see why. You'll find out why that's really important later on in the presentation. So F1 is our range spring force. So that's the force that's pushing down. When we tighten up this or loosen up this knob, it's going to adjust this force on this spring here. F2 is our poppet spring force. So we have a spring underneath the poppet here, and that helps that poppet push up against the seat. So that applies some force. Then we have this force number 3, which is our outlet pressure force, and that's besides the range spring force, it's the most obvious force that we think of, and it's pressing up on this diaphragm here with these blue arrows coming from the outlet. And then last but not least, well, actually it probably is least, is F4, which is the force of the inlet pressure pushing up against the little ledge that's on the poppet. So whatever area is left here. And again, that helps that regulator shut off. So as these forces change, each of these forces is going to do something different, and we'll have a really close look at that later on in the presentation. Before we move to the next slide, what I do want to point out is that since we have this poppet and seat mechanism here, what will happen is as our outlet pressure decreases and this diaphragm moves down because the spring is pushing it down, it does open this valve progressively more and more. So and that's how you get this flow response to pressure demand. So as our downstream pressure, as our flow increases, our downstream pressure is going to decrease, and our regulator responds by opening up to allow more flow and bring that pressure back up. That's how this control mechanism functions internally. So that's a forward-acting pressure-reducing regulator. Similar sort of setup in a back pressure regulator. One thing that you'll see in this diagram that's different is we don't have a poppet in this particular regulator. Some back pressure regulators do have a poppet. In this case, the diaphragm is seating on this O-ring that's on the seat. So a nice simple design. So once again, we have a loading element, which is a spring in this case. It could be a compressed gas. And then we have a seat. Since this is a back pressure regulator, we are maintaining the pressure on the inlet side of the regulator. As that pressure rises and exceeds the setting that we have on this knob, the regulator will open up. This diaphragm will move up because we're overcoming the spring force. Will allow some flow through it, and will consequently bring this pressure back down to the pressure that you want to maintain in your system. Once you're at that pressure balance, force balance, then this regulator will again shut until the pressure increases again. So, and we have the same force balance equation for the back pressure regulator. Again, we're missing the poppet spring force, so we don't have that here in the equation. So we have our spring force, which we adjust with the knob. We have our outlet or inlet pressure force working on the diaphragm coming from the inlet. And lastly, we have the outlet pressure force that's working on this area of the diaphragm, so coming from the outlet. So once again, we have this force balance equation where our spring force will always equal the sum of these two forces. When and I will say this, the spring force will always equal those two forces when operating as intended. One could make an argument that when as this regulator sits here, that yes, this as it's shut off, that this force balance equation isn't necessarily taking place, but we really care about when the regulator is in operation. And so, performance criteria, we're going to talk about, I'm not going to read all these bullet points off, but we're going to talk about these as we move through the rest of the presentation, and give you a really good understanding of what's happening in a regulator. So, the first thing we want to talk about is droop, or some manufacturers will call this flow effect. And what it is that as your flow increases through a pressure reducing regulator, so this is increasing flow on the horizontal axis, and this is pressure on the vertical axis. as your flow increases, your pressure is going to decrease. And there's a very good reason for that. As this regulator opens up more to accommodate more flow, this spring here is going to get longer, right? So it's moving. The diaphragm is moving down. This poppet's moving down. The spring gets longer, so the force exerted by the spring is actually decreasing because we're lengthening that spring, and that little bit of lengthening of the spring does have an effect on the setting, so that force balance equation that we looked at does have an effect. And here's the effect right here on this curve. You see this pressure, as the flow increases, the pressure will decrease. You'll see here as well that there are two curves on this chart, and so inlet pressure. So in this case, this upper curve has got a 500 psi inlet pressure. When you have a higher inlet pressure, you have less droop. Whereas with a lower inlet pressure, this is the same regulator, your droop increases quite a bit. So, and that has to do with you have a much larger pressure drop, much more available mass to flow on this side of the regulator. So it's able to achieve its force balance, without opening so much to accommodate the requirements of the outlet of the regulator. So just a little bit more about droop here. Because the droop is a fairly significant characteristic of a regulator, we do want to understand its effect on our process. So, for example, this particular regulator, if we set our pressure at 60 SCFM, so if we draw a line straight up at 60 SCFM, and we set our pressure at this 65 psi, so we have steady state. We're flowing at 60 SCFM. We adjust our regulator handle. We get 65 psi, showing on our outlet gauge. Now, our process suddenly starts demanding more flow. So, the process wants to now flow at 80 SCFM. Well, what happens is that now our pressure has, that's not a straight line, has dropped to 59 psi. So we've dropped 6 psi for that flow change. Now that may or may not be acceptable for your process. If it's acceptable, great. This is just fine. But you may have a process where you say, oh no, I need to maintain less than 2 psi change. Well, in that case, we want to find a regulator that has a much flatter droop curve than what we have represented here. And that's not a problem. It's just a piece of data that we need to know when we're aiming at a regulator. So some of the things that you can do to prevent or minimize droop is select a regulator where your pressures closely match your system pressures. That's especially on your inlet. If you can get a regulator with a large diaphragm, it's always going to be a more sensitive setup. Or if you can decrease the length of the stroke of the regulator, again, because both those things minimize the amount of change in the spring length. If you can eliminate the load spring, dome loaded regulators have got very flat droop curves. That's a great way to go. We're not talking about dome regulators today. basically a dome-loaded regulator takes the spring out and creates a controlled gas pocket in that cap of the regulator, so that the compressed gas becomes your spring. It's like I said, it's a very flat curve. It comes as a trade-off though. Now you have a more complicated setup. If you need that's great. That's what you should do. But if your application can withstand some change in pressure overflow, a spring-loaded regulator is always the best, most economical choice from a not only initial cost but also a maintenance cost perspective. It's just less complicated. You want to avoid specifying a regulator that falls into this range over here on the far right of the chart. We call that the choked flow area. And essentially what's happening here is the regulator starts to act like a fixed orifice, and you're not getting the control properties of the regulator that you're paying for and expecting. So definitely avoid this choked flow area. It's not a happy place for a regulator to operate. And last, external feedback, and that really has to do more with dome-loaded regulators. But anytime that you can bring the feedback closer to your point of use, you're going to get less lag and less droop. So we talked about how the pressure of a regulator drops when the flow increases. Now we're going to talk about why the outlet pressure of a forward-acting regulator would increase over time. We call that creep, and creep is it's actually quite a scary thing. And when creep occurs, essentially what's happening is typically you'll have a situation where you have a valve on the outlet line of your regulator. That outlet line, for whatever reason, is shut off, and we no longer have flow possible through that line. Well, when a regulator is new, we have a really nice clean seat and poppet here. So it has really good ability to shut off flow. However, as a regulator is in service, over time, debris will come down this line, and you will get debris collecting, or potentially get debris collecting on the seat and poppet, and that's what that debris looks like. So as a consequence, what happens is now you have not a bubble tight seal anymore inside this regulator. So what can happen is, if you have this on a compressed gas cylinder supply, say it's at 3,000 psi, and we go away for the weekend, we shut off this valve. Downstream here, we've got devices that use 50 psi. So over the weekend, we shut this valve off, and the pressure on this side of the regulator can build, and potentially build right to 3,000. So now when you come in on Monday, you have 3,000 psi, sitting in this line here, and when your folks go to open up this valve, they're sending 3,000 psi down the line to your 50 psi devices, which can, it has a number of bad things. First of all, there's just the chance of someone getting hurt, the chance of damaging delicate equipment like analyzers. So it's a definite concern. One of the ways to mitigate the chance of having this happen is really, we highly recommend to not put this shutoff valve here. If you're going to put a shutoff valve in a regulator system, it's always best to put the shutoff valve before the regulator. That way, you still achieve the goal of shutting off your supply, conserving your gas. However, now you don't have this chance of pressure buildup. There are other ways of mitigating this. You could put a relief valve on your outlet. So definitely, if you do need to have a shutoff valve on the outlet of your regulator, make sure that you put a relief valve in there so that you do not end up with having full inlet pressure at your outlet. Some of the other things that are done in order to mitigate some of this debris that can collect. The Swagelock K-Series filters do have a filter screen inside the inlet. You can also install a filter on the inlet of your regulator. So that's always a good practice to put a filter in front of a regulator. Because even clean lines and clean cylinders, over time, they will slough off material and send debris down the line. So creep is definitely a scary thing. So we're going to talk about back pressure regulators now and the flow curve for back pressure regulators. And we talked about droop for the forward acting regulator, and we saw a curve that turned down. Well, now you see that these curves do the opposite. And there's a really simple application or explanation for that, and that is that a back pressure regulator, because it works in the opposite way of a forward acting regulator, this curve is doing the opposite thing. So we call that accumulation. So what's happening here is that again, because we have this spring-loaded mechanism here, the force on the spring, as we have more requirement to flow, and we lift this diaphragm off this seat more to get more flow area, the force on the spring now increases. And because that force increases, that creates the pressure, that causes the pressure to increase along with that. So you see this accumulation curve that it creates. So back pressure regulators, as you're trying to flow more through here, you will see an increase in pressure on your inlet. So something to keep in mind, especially when you have a sensitive process where you don't want to have the pressure build beyond a certain point. We want to make sure that we're having a look at that closely. So the next thing we'll talk about is called lockup. So now, and this applies. We're going to talk about it, with regard to forward acting regulators here. So the lockup is what happens when a regulator actually shuts off flow. And it's easiest to explain by starting with a flowing regulator. So if we start with this regulator flowing at 4 SCFM, and we have a set pressure of 7.5 psi. So we have 4 SCFM showing on our flow meter, and we have 7.5 psi showing on our pressure gauge here. And again, that's always the way that we want to set our regulator outlet pressure. Is we start with our nominal flow rate flowing through the system, then we dial in our pressure. So now we've got the system operating nicely. It's at 7.5 psi. So for whatever reason now, we have a situation where this regulator, this valve shuts off. And let's imagine that it shuts off gradually. So gradually we're following this curve up and over as the flow decreases until we get to very close to zero, and then what happens is you get this spike up, and really what that is the that final closing of the valve. You have your inlet pressure force and your poppet spring force, finally setting that poppet up against the seat, and that's what that effect there is. So now when we look at our outlet pressure gauge, it's going to read here. It's going to read something like 22 psi. So that's something to keep in mind with your regulators is you may have set this regulator last week. Come back this week, you look at it and you see it at 22 psi, and your immediate first reaction is what's going on. Always the first thing to check for is, okay, what are the flow conditions of the regulator now? Did the flow conditions change? And if so, that's more than likely why you're seeing a higher pressure on this gauge. So this is a normal effect that you see in all regulators, something to be aware of, and definitely avoid trying to set your regulator outlet pressure with no flow. Don't do that, because you'll always have to chase that regulator once it is flowing. Okay, so Joule-Thomson effect. The Joule-Thomson effect is something that we all experience every day. It's what takes place in your refrigerator and in your air conditioner. And what it is when we expand a pressurized gas, in most cases, that gas cools. And it can cool to a point of dropping below the freeze point of whatever fluid you have around it. In this case, it's moisture in the atmosphere. So you see this ice accumulation on the outside of this dome-loaded regulator, and that in and of itself is not an issue. It doesn't. It's not going to stop that regulator from functioning. However, if you were accumulating frozen materials inside the regulator or inside this outlet line, you would definitely be impacting how your system operates. So, we do want to think about, how can we compensate for this? And there's really two ways. We could preheat the gas. So we could put a heat exchanger before the regulator to bring that temperature up to a point which, once we would run the gas through the regulator, that it would balance out that heat loss effect. Or we could use two-stage or even more multiple stages of pressure drop, because what that does is, as you add more stages of pressure drop, it allows the environmental heat to soak back into this system. So if you could take that pressure drop and divide it out, so you only have half as much cooling in each drop, you have twice as much ability for the environment to soak back into this regulator and give back heat. You could heat a regulator as well. So that's another way of doing the job. But two-stage and multi-stage regulation is quite effective in a lot of cases. So we want to talk about optimal flow range. So at this point, we've talked about a number of different performance criteria of a regulator. Now we're going to bring all that together in this chart here. So in manufacturer's literature, you are either going to see large tables of numbers, or you'll see graphs such as you have in front of you. And these are this is the information that folks use in order to choose a pressure regulator. So in our literature, we use graphs, and we find that it's just a little bit easier to absorb the information in a graph and to select through that. And what we want to do when we're looking at potential regulators is look at these curves, and we really want to avoid working in this lockup range. We want to avoid working in this choked flow range, over on the right. I want to really stay in this kind of nice flat center section of the curve. Now you'll notice that this while this regulator at 2200 psi, we could use it over this wide range of flows. If we take that same regulator and only have 1000 psi on the inlet, now we only have the ability to use it for this range of flow, and really we can work up into this area over here, right? We really want to avoid this lockup tail. But you can see where inlet pressure has a huge effect on the amount of flow that you can put through a regulator. And one other thing that I want to point out here before we move to the next slide is that you'll see here we have blue curves, and then we have black curves up here. The difference in these is the different outlet ranges of the regulator. So we represent these in one graph. So you really need to, when you're looking at the regulators, pay attention to the chart titles, and that'll explain to you why there's blue lines and some black lines. So I want to get back into the math of a regulator and talk about supply pressure effect. And we talked about the different forces in a forward acting regulator. When a regulator is in its steady state, when it's flowing and there's no flow or pressure changes going through a regulator, your spring forces F1 and F2 are essentially constant. So when that's the case, any changes in F3 and F4 need to be equal and opposite to each other. So why that's important is we have this thing called supply pressure effect, where when our supply pressure changes, and typically our supply pressure, say on a compressed gas cylinder, it drops and then it'll pop back up and then drop as we change the cylinder out. Or an air compressor would does the same sort of thing. Well, as that pressure goes up and down, as that supply pressure drops, there's this weird thing that happens where the outlet pressure increases, which is not intuitively obvious. But if you have an air compressor that you're able to look at, if it has a gauge on the tank and a gauge on your regulator, you will notice that effect, that as the tank pressure increases, that the outlet pressure of the regulator decreases. Now, why is that important? Well, it's important because it can have a very large effect on your outlet pressure. If you're starting with 3,600 psi in and you're 50 psi out, there can be a significant effect on 50 psi if we don't do something to mitigate that effect. And that a really nice mitigation is a two-stage regulator, which is what this regulator in front of you is. Now, and I'll explain why that is in these slides here. So here we have that two-stage regulator represented by two individual regulators. It's essentially the same thing, they're just not built together. We're starting at 3,600 psi. This regulator, for this example, has a 1% supply pressure effect. That means that for every 100 psi of change on the inlet, you'll see 1 psi on the outlet. Okay. So As we use our compressed gas cylinder from 3,600 psi down to 2,000 psi, or down to 1,600 psi, since we're losing 2,000 psi, 1% of 2,000 is 20. That means that our pressure on this side goes up by 20 psi. So, yeah, if we were set at 50 psi here, that'd be a pretty significant change from 20 to 70 psi. Now, because we have two-stage regulation, we're at 500 psi. So that 500 psi goes up to 520. Again, we have 1% here, so 1% of 20 is 0.2 psi. So on this side of this regulator, the pressure has gone down by 0.2 psi. So ultimately, while we started at 50 psi on this outlet, we've gone down only by 0.2 psi, even though our inlet pressure here has dropped by 2,000. So that's the magic of two-stage regulation, and why you want to use that with compressed gas cylinders. And that is why products like this exist, where it has two regulators built into one, and you have the ability to set your outlet pressure, and the factory sets that first stage pressure cut to whatever makes sense. So as our example, this example is 500 psi. So that's supply pressure effect, and that can have a significant effect on your analyzer or your application, if you're running off compressed gas cylinders. So the last thing that I want to talk about today is venting options. I'm going to start by talking about this, the area inside this cap here. So the area inside the spring cap, it needs to be vented, right? Because it's a working area. Typically, you're either going to have a vent hole underneath your cap, or you might have a threaded fitting into the side. Okay, and we'll talk a little bit more about those differences in a moment. The other important thing to know about venting is that some regulators have the ability to what's called self-vent, and what that is into the diaphragm mechanism, there is the ability to vent a small amount of excess pressure from the outlet side of the regulator. Okay, now this is really intended simply for adjustment purposes. So when you're adjusting your pressure, that you can adjust you can turn your handle counterclockwise until you hear the pressure relieving. Then you can dial your handle back in clockwise and achieve your lower set pressure. That's really the intent of this mechanism. It's not intended to be a relief valve or a safety device. It has no rating for flow. So please, if you're concerned about creep on the outlet of your regulator, this is not a mitigation for that. So the different options that we have for venting are, first of all, there's no self vent and no captured vent. So basically what this guy here is that it doesn't have this mechanism in it. It simply has this vent hole underneath the cap that anything going on inside this area here is simply vented to the atmosphere. So that could be a concern if you're dealing with something that's highly toxic, and if you, or say pyrophoric, and you want to have some mitigation for, if there was a failure, in this diaphragm. So what you could do is have a captured vent on the no self vent, and what that does is removes this hole and replaces it with the NPT thread and seals the stem to the cap. So now if something were to happen, anything inside this cavity, you could send it to a safe place. The next thing we want to talk about is the self-vented options, and we have the same sort of capturing options. In this case here, we have no captured vent, just vents from underneath the handle. Whereas this self-vent option has a captured vent. Same thing is that if it does self-vent, that it's going to be connected to a system where you could manage that vented gas. So those are the venting options that we have. So really brief review. We talked about the fact that regulators are for controlling pressure, not for flow. And one important thing that I want to point out is that regulators are not intended to be a shutoff device. When they're brand new, will they shut off? Sure, but they're really not intended to be used that way. They're a dynamic device that really requires that it be flowing. It's not intended to shut off for long periods of time. We talked about the two types of pressure regulators, forward and back. We talked about the different elements within the regulator, and we looked at the flow curves and regulator performance. Are there any questions that have come through, Jay?
Yeah, there were a few, Rich. I handled most of them in the chat, but
Okay.
if you want to elaborate on any of them, feel free. I don't know, can you see the chat at all, or shall I read them to you?
If you could read them, then that would help everybody, I think.
Sure. So the first one was what materials are the regulators available in? I described our common offerings of stainless steel and some of the alternative materials that were available with the K-Series product line.
Okay. All right. Yeah, and definitely, our literature, has got some really good information there, and if you have very, stringent requirements, please give us a call. We can work through that with you and do some material compatibility checks as well.
The next one was optional O-rings for the regulators. I highlighted the standard FKM that's available in most products, and then CalRes kind of being an option for more aggressive media with the K series.
Right. Yeah. Exactly. Again, when there are applications that we need to have a closer look at, again, let us help have that conversation with you. Okay.
Next one was a spring load versus gas or dome load. So you spoke to that, but any thing you want to add, feel free.
Yeah, dome loaded regulators are great. They do a really nice job of controlling your pressure over a wide range of flows. They have some really great feedback options. You need to keep in mind that with a dome loaded regulator, you increase the complexity of your system. So you really need to have a good reason to use a dome loaded regulator. That's just something to keep in mind, that it does have that complexity, but in the right applications, it is absolutely a great device to have in there.
Next one was where would a poppet be used in a back pressure regulator?
Okay, so the basically where that's probably easiest for me to bring up the slide of the back pressure regulator. So I will group back pressure regulators. There we go. All right. And will that work? Oh, all right. Well, that's not working for me. Let's do it this way. All right. So in this particular image, you see where the diaphragm is actually acting directly on this O-ring. What some back pressure regulators will have is that you would have this, rather than have the seat directly underneath the diaphragm, the seat would move further down in the body, and then you would have a poppet attached to the diaphragm, or working up against the diaphragm with a spring and working into a seat. So much like you have the pressure reducing regulator that is working up against the seat this way, you'd really just flip this poppet and seat mechanism around and have it working in the opposite direction. And really, it comes down to, why would you do it that way? It really is, as you get to larger flows and wanting more control over your flow, that's when you're going to end up with a poppet style back pressure regulator.
So then one just came in, what's the difference between flow and pressure?
Well, really the difference is this, is that, I mean, they're tied, those two are tied together. So when you have your process, in fact, if we go back to our first slide here, let's see. I kind of aid in the discussion. So with your process, you and regulation, you want to maintain your pressure within the process. You want to supply it with pressure. You want to also maintain that pressure as it leaves the process. And the process is going to require a certain amount of flow. So the relationship is this, really, is that it really is process dependent. The regulator really is responding to what your process requires. The flow through the process really is determined by the process. So more than likely, you will have some sort of consumption going on. You'll likely have a control valve in here that's opening and closing, controlling flow, and that's really where your flow control is coming from. The regulators really it's simply going to respond to those changes in the process. So when the process demands more flow, the regulator is going to provide more flow and attempt to maintain that pressure. And vice versa, as the process demands less flow, your regulator will close down and provide less flow in order to maintain that pressure on the outlet. I hope that answers the question. If it doesn't, then please get in touch with us and we can have a little bit more of a discussion.
Excellent, Rich. And the last one that just came in was, do you keep regulators in stock, and what about gas fittings?
Okay, so we do have some regulators in stock, but generally, in a lot of cases, because there are so many different pressure ranges and requirements, we tend to fill those on order. So if there is a requirement or something that you have that you typically would want us to stock, give us that feedback and we'll make sure that we have that particular item in stock.
And gas fittings.
Okay, and similar with gas fittings, there are some that we have, but typically, there are so many different gas fittings that we do typically source our gas fittings either from Western Enterprises or from Matheson. So again, we can address those specific requirements as they come up. So it's better to ask early to make sure that we do have what you require. So our stock is not vast, but we do have a few things.
And that was it. Rich, yeah, that concludes the questions.
Okay, good stuff. And again, if there are other questions, please get in touch with your account manager. We're always, more than happy to help and to help with regulators. So thank you very much for your time today. For further information, we will be sending out a follow-up email to everyone, and as well, our website links will be in there, and the second link will take you to this page that has our regulator information, and this regulator catalogs link I wanted to show you really quickly does show our regulators, and also shows our pressure reducing flow curve technical bulletin, where you'll find all the flow curves for our regulators, and as well a flattening the curve document as well, an article that was published that goes into more detail about how we can flatten that droop curve. So with that, we will bring today's presentation to a close, and look forward to the next time we do a presentation.